Hello my dear children of class 11 science. Today we do again continue with the chapter, same chapter that we were discussing the last class, simple harmonic motion. Okay, and today we complete this chapter, and especially in today's class we do the last theoretical topic, okay, an important topic, graphical representation of total energy of a particle in simple harmonic motion. Yes, now in the last class till yesterday, okay, that means on the last class we had done up to the total energy of particle in simple harmonic motion, and we calculate the relation of total energy in terms of kinetic energy and potential energy. Now children, you know that the kinetic energy of particle at any certain time, as we had done in the last class, is given by half k a square cos square what omega t plus phi. So this is the relation here, we have done it. Okay, and you know k we have taken as what, m omega square. So the a square, and this is cos square omega t plus what, phi. But the same kinetic energy can be written in terms of what, the displacement of the particle. Now for that, since you know that y we have taken as what, y equals to a sine omega t plus phi. Yeah, this is the displacement of the particle we have taken in terms of the epoch of the particle. So if I make squaring both sides, then it will be y square equals to a square sine square, okay, omega t plus phi. Now what actually I am trying to do is I am going to express this k in terms of displacement, so that I need to eliminate this cos square phi. Okay, so how to eliminate this cos square phi? Because we know that cos square omega t plus phi, okay, is equals to 1 minus sine square omega t plus phi. Okay, now cos square theta minus plus sine square theta is 1, so cos square phi omega t minus phi equals 1 minus sine square phi. Okay, so instead of this quantity, now I write down what, this quantity. Okay, now I will be writing now the relation as k equals to what, half m omega square a square. Now this cos square omega t plus phi I will put in the relation, so it will be 1 minus sine square, okay, let me write curly bracket, omega t plus what, phi. Okay, now what is sine square omega t plus phi? That can be written even as the relation as 1 by 2 m omega square a square. Okay, now I'll put first bracket only 1 minus. Now see, y square equals a square sine square omega t plus phi means then sine square omega t plus phi will be nothing but y square by a square. Yes, this a square will go in the denominator also. Now let me take the LCM. Now your LCM will be 1 by 2 a square only, but there is a quantity m, half m omega square a square, and it will be how much, a square. The LCM is a square, so it will be a square minus what, y square. So that a square is square cancel out. So finally you can see the kinetic energy is given by half m omega square, okay, with bracket how much, a square minus what, y square. So this is the expression of kinetic energy of the particle in terms of displacement at any instant of time, in terms of displacement, but at any instant of time. Okay, similarly we can write the potential energy also of the particle. And children, we have done the expression potential energy in the last class also. Similarly I write down potential energy, potential what, energy. And potential energy is basically symbolized by letter U, and potential energy, yes, we have done in the last class yesterday, is equals to half k a square cos, okay, this is sine square omega t plus what, phi. So this is the expression of potential energy that we have done in the last class. So let me again write the same potential energy in terms of displacement. So I write in half. Now this k, small letter k means m omega square, and there is already a square. Now sine square omega t plus phi, see, I can write again this as y square by a square. So that a square is square cancel out. So u is now half m omega square and y square. Now you can see the expression of what, potential energy even given by half m omega square y square. And this is also the potential energy of particle at any instant of time when the displacement is known. Now from these two relations, we can easily represent the total energy graphically. Means now we do the graphical representation of total energy, but in terms of this kinetic energy and what? Potential energy. Okay, so for that, let me just do the case 1. Let me just do this way, like case 1. If I take y equals to 0, if y is 0 means the displacement 0, and displacement 0 means, remember this, the particle is in which position? Equilibrium position. This is when the particle is at equilibrium position. When the particle is in which position? Equilibrium position or mean position. Then we can calculate the potential energy. Your potential energy will be how much? Simply half m omega square. Now displacement is 0 means you are at 0 square, and any quantity multiplied by 0 means 0 only. So u equals to what? 0. Now at the same time we can calculate what energy? Kinetic energy. Now kinetic energy is given by this expression. So I write now half m omega square a square minus, now y I put at 0, so 0 square. So it will be half m omega square a square. So this is the kinetic energy, which is 1 by 2 m omega square a square. And remember children, this kinetic energy which we have calculated is maximum. Now why kinetic energy maximum? Because the body have a maximum displacement that is equals to amplitude, and this kinetic energy is what? Maximum. So one of the first position that we took is equilibrium position when the displacement is 0, and we saw that in displacement 0 potential energy is 0 and kinetic energy is what? Maximum. Now the second position that we take is when the particle is at one of its extreme position. In a displacement, that there are two positions, one is mean position and another is what? Extreme position. So extreme position means the maximum displacement, and the maximum displacement equals to the amplitude of the particle. That means the maximum displacement y is equals to a, the amplitude particle, on the positive side, or y equals to minus a, the amplitude of the particle on the negative side. So under this case also we calculate the potential energy and kinetic energy. So your potential energy will be given by u. You know what is the formula? The formula is what? Half m omega square what? Y square. Now let me just put y is either a or minus a. So if I put either a or minus a, but the square is there, so it will be always a square. So half m omega square a square. So u equals to half m omega square a square. Okay, so this is the potential energy of the particle, but this potential energy is maximum. This potential energy is what? Maximum. Similarly, I calculate what energy? Kinetic energy. So similarly, kinetic energy also I calculate. Okay, your kinetic energy expression is k, and k equals to what? Half m omega square a square minus y square. So this is the formula that we have done it. Now let me substitute y as a or minus a. Even out here also, if you put y as a or minus a, square is there, it will be a square only. So half m omega square a square minus a square. This is the case when you substitute y equals a or minus a, but it will be a square only. So a square minus a square will cancel out. So half m omega square into 0. So any quantity multiplied by 0 means 0. So k will be equals to 0. So your kinetic energy will be 0 when the particle reaches to the what position? Extreme position. Well, the potential energy of the particle become maximum. But even you calculate the kinetic energy, potential energy, but we calculate the what energy? Total energy. And you know the total energy, as you know, total energy means E, and E equals to what? Kinetic energy plus potential energy. 0 plus the potential energy, how much? Half m omega square a square. And children, in the last class